Hello everyone, my name is Fernando Navarrete. I am currently a third year electrical and computer engineering student here at UCI. Today I will be talking about communication systems in Internet of Things, also known as IoT. The main idea of this presentation is to talk that IoT is not just about sensors and gadgets, but it also talks about how important communication network is. I will start off with a few things such as what is IoT, some real world examples, then I'll show how 5G and machine learning support massive IoT. After that, I will talk about the future of 6G architecture and security, and finally, I'll end off with opportunities for us EE students pursuing this field. Okay, now for some background. What is IoT? First thing is IoT stands for Internet of Things. So instead of connecting phones and laptops, we connect lots of small, low power devices over the internet. These devices can be sensors or actuators in our homes, like and cars and cities. They usually talk using machine to machine communication, which means devices send data to other devices and to gateways without a person in the loop. On the figure on the right shows the main idea: many devices at the edge, a network in the middle, and services in the cloud. So IoT is really just a huge network of small devices that quietly share data throughout the background. Okay, what are some real world examples? IoT already shows up in a lot of places that we know. For example, in smart homes, appliances like lights, thermostats, and cameras connect over the Wi Fi or other wireless links so we can control them remotely. Another element is intelligent transportation, as cars and buses share data to support autonomous driving and traffic management. Another aspect is a smart city, as smart cities combine many of these ideas, such as homes, transportation, and buildings that are all connected to monitor the energy use and traffic in the environment. There's also aspects within industrial IoT, where factories put sensors on machines to track the performance and prevent failures. There's also smart healthcare, where medical devices and wearables send patient data to doctors and hospitals. All of these are examples that depend and rely on communication between devices and networks. Now, moving on to the importance of communications. Because there are so many devices, communications is critical. As one of the papers I read by Akpaku, one of the co-authors, they said that IoT's vision can only be realized if many telecommunication techniques work together to connect machine-type devices. IoT heavily relies on M2M communication. The author also describes the need for seamless communication medium so devices can exchange data without any human help. There's also estimated to be around 7 billion devices that will connect via cellular IoT by the year 2025, so this year. So if we don't design good communication systems, a lot of these IoT applications may not be able to be scaled or work properly. Now moving on to IoT and its regards to 5G. Older cellular standards like LTE were made mainly for smartphones and mobile broadband, so they weren't designed for low power, low data rates such as IoT devices. So, according to a survey, 5G was also introduced to overcome these limitations and provide a better platform for IoT. 5G adds different service categories that one of which that's really important, which is machine type communication, which is or also known as MMTC. MMTC targets large scale IoT connectivity, thousands or millions of devices sending small packets. 5G also gives us the basic tools to connect or a huge number of IoT devices. Now moving on to some challenges seen in IoT communications. Even though with 5G we have many benefits, there are still some challenges seen with massive machine type communications. First, we need highly scalable cellular networks that still provide good coverage. As more IoT devices arise, the radio access signaling channels can become more congested. Secondly, IoT devices send small, random, and sporadic traffic, and they are limited by battery life. Traditional cellular systems were not built for a huge number of tiny battery-powered devices that wake up and send short bursts of data. Third of all, IoT applications have very different quality of service requirements. Some are delay tolerant while others need high reliability and low latency. There is no one-size-fits-all protocol. These issues motivate more intelligent ways to manage these networks. Okay, now let's move on to machine learning and IoT. With the rapid rise of machine learning, it is proving to be a key tool for ultra-dense IoT networks. So instead of relying on fixed formulas, ML models can learn from real traffic data and adapt to how networks behave. For example, they can predict traffic patterns and network load, so base stations can choose better times for devices to access the channel. This helps reduce congestions and collisions in MMTC. Machine learning can also assist with resource allocation and quality of service adaptation, deciding how to share bandwidth so different applications meet their latency and reliability goals. So, machine learning basically acts as an extra brain on top of the communication systems that are being in use, helping it adjust to the complex behavior of IoT systems. Now, moving on to the evolution of 5G to 6G. So, even with 5G and machine learning, there are still some open research problems. So, even though 5G was meant to support new massive and critical IoT services, there are still some limitations in managing these networks, especially as devices keep growing in number. So there's issues arising from exponential traffic growth and a need for better congestions and quality of service solutions. These issues lead to researchers to think about a new technology such as 6G. So 6G is not only about higher data rates, a major focus is on intelligent and secure communication, especially at the edge of the network. One example is a new trust architecture that I'll show in the following slide. Now let's begin to talk about the 6G architecture. So, research proposes a new idea on an adaptive trust architecture for 6G IoT. The figure shows three-tier edge cloud continuum. In tier 1, we have the local edge, where IoT nodes connect to nearby edge devices. In tier 2, there is a multi-axis edge layer, such as MEC servers near base stations. Tier 3 is the cloud, which handles heavy computation and storage. At Tier 1, they place an Adaptive Zero Trust Manager, or also known as AZTM. It acts as a trust anchor for IoT devices and enforces zero trust security to close the data source. AZTM updates trust scores for each device based on its behavior. It also logs these decisions in a lightweight blockchain ledger and uses elliptic curve Diffie-Hellman key exchange to set up a secure communication key. Because this runs at the edge, it provides a low latency, scalable security for dense 6G IoT devices. Okay. Now let's move on to some potential security issues. So, why do we need this kind of trust system? First things first, IoT devices often carry sensitive data and may control physical objects. So there's this emphasis that security and privacy are very important to ensure that information and devices are properly monitored and controlled. Secondly, 6G's ultra latency and massive connectivity create complex security challenges, as with distributed IoT deployments need adaptive mechanisms to maintain trust in dynamic and distributed environments. Third of all, many current security frameworks, such as some heavy blockchain systems, rely on high performance computing platforms and energy extensive protocols. Those are not practical for tiny IoT sensors or devices. This is why we need to look for lightweight and minimal solutions for AZTM in 6G and also in 5G. Now, looking into the future. So, what does the future of IoT communications look like? On the 5G side, there are suggestions that networks will become more software driven using SDN and NFV to make IoT connectivity more flexible and scalable and to handle congestions more intelligently. On the machine learning side, we can expect ultra dense IoT networks to rely increasingly on low complexity machine learning algorithms for access control, traffic prediction, and quality of service management. Also on the 6G side, we can envision edge-centric zero-trust architecture that use AI and machine learning to adapt a trust and security policies over time. Overall, we're moving from 4G to 5G towards 6G with more devices, more intelligence, and stronger security. Now, what are some opportunities for EE students? What does this all mean for us EE students here at UCI? One path is to specialize in communications. In that track, we learn about modulations, coding, wireless systems, and networking protocols, all of which are building blocks that IoT depends on. Another path is to take some courses that may help that I've mentioned before, such as machine learning related courses, such as EECS1 here at UCI, which introduces data and knowledge science and basic ML concepts you can later apply to networking and security. It also helps to build projects and join clubs. For example, in the IEEE OPS, which is an embedded systems project-based club, I built a small weather station project shown here on the right, using two ESP32s that connect over the Wi-Fi. That uses community sensor and light detection, and sends that data via the Wi-Fi to another ESP32 that outputs all of that information onto the LCD screen. Projects like this, that are mini versions of real IoT systems, help connect the theory from class to actual hardware and communication practicality. Now, to conclude, communications is an integral part of IoT, since billions of low power devices only become useful when we design networks that connect to them reliably. 5G and machine learning are key technologies today that allow massive IoT deployments and help manage congestions and quality of service, also known as QoS, right? And now looking ahead, 6G aims to add intelligent, secure trust at the edge with architecture like AZTM, providing low latency security for huge IoT networks. Now, for us EE students, learning communications, machine learning, and security and building hands-on projects puts us in a very good position if we want to work in this field and the next generation of IoT devices and systems. For me personally, this is why I'm drawn to the communication specialization here at UCI. I like that communication sits right between hardware and software. We work with real circuits and antennas, but we also design the protocols and algorithms that move the bits through the air. When I build projects like my small weather station, I can see how a single sensor fits into a much bigger system. Studying communications lets me scale the idea up, from one board on my desk to thousands of devices in a smart city or a rover or a satellite. My goal is to keep what I learn in class with embedded projects, research, so I can help design the future of IoT and 6G systems that are not only fast, reliable, and secure, and useful for real people. Thank you for listening for my presentation, and here are my references, and thank you.